And our next presentation is one of our own at APL, Brandon Haber. He's presenting on Dragonfly Flight Software Overview. Brandon.
Hi there, am I coming in?
We can hear you and we can see you.
Great. All right, hello everybody, I'm Brandon Haber. I'm the flight software lead for Dragonfly being built here at APL. Dragonfly was selected in 2019 under NASA's New Frontiers Planetary Exploration Program to explore Saturn's moon Titan in the 2030s. And I'll be giving an overview of the mission and the flight software impacts today. Next slide, please. So today we're going to talk about the destination and science goals of Dragonfly, our mission architecture, our unique mobility system, and some of the impacts all of those things have on our flight software. We're just a few months prior to our flight software requirements review though, so everything in this talk will be at a fairly high level from a technical perspective. But I hope to show you why Dragonfly is such an exciting mission and why the next few years of development for us will be so interesting. Next slide, please. Every aerospace vehicle is shaped by its environment, and Dragonfly is a unique vehicle largely because Titan is such a unique place. It's larger than both Mercury and our moon, but has a lower gravity. It also has the second highest pressure atmosphere for a rocky body in our solar system, just behind Venus. It's also very cold though. You can see that negative 290 degrees Fahrenheit. So the chemistry and geology there may look a little bit familiar, but it's actually a very alien world. Next slide, please. So why do we want to explore Titan at all? Well, the answer is that there's a lot of unique chemistry. There's methane cycle, like water on Earth, with liquid methane on the surface in lakes, which can condense into clouds and fall back as rain. There's photochemistry in the atmosphere, with solar energy interacting with atmospheric compounds, and those compounds interacting with a complex surface. All in all, there's lakes, riverbeds, and dunes, familiar geologic processes, but shaped by different components in a different gravity field under a different atmosphere. There was also likely liquid water on the surface in the past from impact heating, among other sources. All in all, Titan's chemistry may look similar to Earth's billions of years ago before life arose. Next slide, please. So where on Titan are we going? There's dune seas throughout Titan's equator. And those dune seas are driven by winds and collect compounds from all over Titan's surface. So there's a lot to see there. For us also, there's some large flat areas to land. The pictures on the left are the closest Earth analog to Titan's dune seas, the Namib Desert in Africa. And the picture on the right is Cassini-Vince data of our landing ellipse. And just to the north is Selk Crater, our ultimate destination. Next slide, please. So now that we've talked about where we're going, how are we going to get there? Our mission is going to launch in early 2027 with an eVega trajectory. It's going to launch from Earth, fly by Venus, and then Earth again in order to pick up enough energy to go out to Saturn. Unfortunately, Jupiter's in the wrong part of the solar system, so we won't get any gravity assist there. There's also a direct atmospheric entry in late 2036, so there's almost a 2-year-long cruise duration. Because Titan's gravity is so low and the atmosphere is so dense, the atmospheric entry sequence is actually about 2 hours long, including over an hour on our drogue parachute. So with apologies and good luck to any of the Mars 2020 people that may be listening, I wish you all the best of luck on your EDL next week. But we've joked on Dragonfly that we don't have 7 minutes of terror. Instead, we have 2 hours of mild anxiety. I'll be a little bit more than mildly anxious when we finally arrive at Titan, but it's true that our entry sequence looks very different. Next slide, please. So what are we sending all the way out there? Well, we have 3 flight system elements. The first one is that cruise stage there that you see on the left. And that's all the things that you'd think of when you normally think of a spacecraft. We've got thrusters, star trackers, sun sensors, and so forth. In the middle is our EDL assembly, entry, descent, and landing assembly, and that contains all of the things necessary to actually get us through Titan's atmosphere and get to the surface, like a heat shield, back shell, and parachutes. And then, of course, we have our lander. And the lander contains all of the scientific instruments as well as our mobility system. It has a multi-mission radioisotope thermal generator to charge the battery to power flight and science activities. We also keep the waste heat from the MMRTG around to keep us from freezing in Titan's cold atmosphere. We have direct-to-Earth communication with HGA articulation used to target the cameras that are mounted on top of the HGA platform. We have scientific instruments that can measure things on the surface and in flight. And you can see there that picture of the lander in the surface configuration with the HGA deployed. Next slide, please. One more back, sorry. Yep. So here's our instrument package. We have DragMet, which is the geophysics and meteorology package, which is a collection of a lot of different sensors. But one in particular is really interesting, and that's a seismometer that will be lowered on a winch to Titan's surface. That seismometer will be the first seismometer flown to an ocean world and the first in the outer solar system. DragMet also includes hydrogen sensors, methane sensors, electric field sensors, and a few other things. We also have DRAMs. That's our mass spectrometer, which will give us the molecular composition of samples that are fed to it by the Draco drills that will be able to drill into Titan's surface and feed material into the DRAM's mass spectrometer. There's also DragonCam, which will contain multiple cameras. We have downward-facing cameras, which can take pictures on the surface and in flight. We have microscopic imagers to take images on the surface. We have forward-facing cameras, again, also to take images on the surface and in flight. And those panoramic cameras that I already mentioned that are mounted on top of the high-gain antenna. We also have Dragons, and that's our gamma-ray neutron spectrometer. And that'll give us the bulk elemental composition in the surface below the lander. Next slide, please. So we have a mobility system that's very unique for Dragonfly. The problem is that we want to sample parts of Titan that are all over the place. Titan has a low gravity and a very dense atmosphere. So it turns out all forms of flight are much more efficient on Titan. Our instincts of looking at flying vehicles are shaped by Earth gravity and Earth atmosphere. But of course, Dragonfly isn't going to fly on Earth and in fact can't lift its own weight. So Dragonfly breaks a lot of our perceptions. You can see on the bottom left there, that's Dr. Z.B. Turtle, the principal investigator of Dragonfly, holding a full-scale rotor from one of our early tests. And so that gives you an idea of the sense of scale of the Dragonfly vehicle in its dual quadcopter configuration that will allow itself to fly around Titan. Next slide, please. So our exploration strategy for Dragonfly is a leapfrog exploration strategy, which takes advantage of the fact that we can fly for very long distances. We'll take off, fly over the dunes at a cruising altitude that is above all of them. So we're not swerving in between any dunes or hills or anything like that. Then we'll be able to go down to a lower altitude and scout out a potential site before rising back up to our cruise altitude and coming down to a landing that we had previously scouted out for the balance of scientific objectives and safety to land. And then as we continue doing these leapfrog strategies, we'll be able to always have a scouted landing site that we know is scientifically interesting and safe to land. And as we build up these leapfrogs, we'll be able to transit from the dune seas towards South Crater. Next slide, please. So we have a big lander, and it's worth talking about some of the numbers. The lander itself is about 750 kilograms and about 3 meters long. It's going to fly for on the order of about 30 minutes at a time with a net range of about 4 to 6 kilometers. And that net range is inclusive of our leapfrog. So if we wanted to fly in a straight line, we could fly for about 15 kilometers or so. We're going to do about one flight every month, every Earth month, which is about 2 Titan days. Our prime mission surface timeline is about 3 years. So our total planned mission traverse is about 180 kilometers. And that's designed to take us from approximately the southeast edge of that landing ellipse that you see, all the way up to the edge of South Crater to the north. Next slide, please. So as a note on our flight software architecture, we're still in the very early stage of the program. Our flight software PDR isn't until mid-2022. We have assumptions about the flight computer and operating system, but we haven't bought them yet, so we can't really talk about them yet. There are some highlights, though, that we do know. We have 2-sided avionics, a prime side and a redundant side, residing on the lander itself. There's no separate flight computers on the EDL assembly or cruise stage. It'll all be controlled directly from the lander. We'll be using CFE and an APL-developed system called Flight Software System. And Flight Software System gives us commanding support, telemetry, support for the CCSDS file delivery protocol, a rule-based autonomy engine, recording and playback, and more. The code lineage for Flight Software System dates all the way back to Messenger and New Horizons, with some design heritage back to even earlier missions. And this code has been modified by every mission since. It's worth noting that Messenger launched in 2004 and New Horizons in 2006. So some of that code was written in the early 2000s and will hopefully be operating on Titan in the late 2030s. So that's almost a 40-year lifetime for some of that code. Next slide, please. So now let's talk a little bit more about the flight software. I'll go into a little bit more detail about each of these things. First of all, we of course have to fly through the atmosphere, which means compared to a spacecraft, we have relatively fast closed loop guidance, navigation, and control. Additionally, we have a relatively fast time to criticality for many of our fault situations. And our definition of a safe mode is a little bit complicated when we're flying around Titan. We also have navigation challenges. Of course, we don't have GPS all the way out there, so we have to have some form of terrain relative navigation to make sure that we can land precisely. We're also not landing on any sort of prepared surface, so we need to be able to do our own hazard assessments for each of our repeated landings. Our power source is an MMRTG, which means we need to save as much energy from the MMRTG as possible to charge our batteries, which means we need to power down as much of the avionics as possible, which in our case includes all of the flight computers. So the flight software will be shut down and not running at all through most of Dragonfly's lifetime. And that means that we need to save and reinitialize that state often. We also may need to boot up very fast in case of faults during hibernation that flight software needs to react to. We're also going to be very far from Earth, which means that not only do we have a low uplink and downlink rate, but we also have a very long round trip light time. And I'll talk about some of those impacts on later slides. Next slide, please. So let's talk about our GNC impacts. We have some fast closed loop GNC. Our cruise guidance and control application will be running the spacecraft until it gets to Titan. And that's the fairly standard stuff that I already talked about: thrusters, sun sensors, star trackers, and the like. That is going to run at somewhere around 20 hertz. But we also have a mobility guidance, navigation, and control application, which will have multiple rates, including a rated up to 100 hertz or so, and it'll be operating on 200 hertz IMU data. We have some intracycle latency sensor and actuator latency requirements as well, meaning that we have to take in data from the IMU, feed it through our GNC algorithms, and then output rotor commands and other actuator commands within that same 10 millisecond cycle. That means that we've got some interesting complexity on the part of our flight software schedule. We also have terrain relative processing being hosted on the main flight computer. And the terrain relative processing will do our final flight navigation solution. It'll process radar and altimetry and velocimetry, and it'll also do our final landing site hazard assessment. Those tasks are much more computationally complex and much lower rate. So those tasks will be running in the background at the same time as our much higher rate GNC loops on the same processor. All in all, our flight software schedule is likely to be pretty complex when we're all done. Next slide, please. From a fault management perspective, there's no easy safe modes when we're flying over Titan. What goes up must come down. We have to land somewhere, but not everywhere is safe. So we're defining some different fault cases with different responses. For some faults, we may continue our leapfrog flight as normal. For others, we may land at our nearest pre-scouted site, which might be a ways away depending on our point in the flight profile. For others, we may land quickly, but with a balance of risks, we may still want to do a hazard assessment sweep before we land. And for others, we just want to land as quickly as possible. It doesn't matter where. It's also true that our time to criticality for many of these faults varies greatly depending on our point in the flight plan. For example, we need to limit landing gear loads on each of our repeated landings. And if we lose control of a sensor or actuator very close to landing, we need to respond to that fault very rapidly in order to make sure that we stay within structural constraints. We also want to have pre-flight built-in tests, including a ground-in-the-loop go, no-go that will be executed and received by the lander a few hours before takeoff. Those pre-flight built-in tests will be the final check that Dragonfly does fully autonomously before it takes off. And that follows the old aviator saying that it's always better to be on the ground wishing you were in the air than in the air wishing you were on the ground. Next slide, please. From a flight navigation perspective, there's also some pretty interesting impacts to flight software. We're going to have flights of 12 to 18 kilometers total distance and about 30 minutes, which means that our IMU-only navigation isn't stable enough. The errors would build up too much in order to target the landing sites that we want to for scientific purposes. So we have a form of terrain relative navigation, which includes breadcrumb images from previous leapfrog flights. This allows us to build up breadcrumbs taken from our navigation cameras as we fly over Titan, so that on future flights and on the back pass of a leapfrog, we can follow those breadcrumbs back again. Next slide, please. We also have to do our own hazard assessments to make sure that we're landing on a safe area. So we have flash LiDAR processing on board. This flash LiDAR processing will allow us to detect slopes and hazards. It's worth noting that this is not hazard avoidance. We're not going to target a landing site and then swerve away at the last second from a rock. Instead, what we're going to do is a low altitude flight pass over an intended landing zone and build up a map with this flash LiDAR data that includes our slopes and potential rock hazards. Then we'll process that map in order to select a landing site that is the safest possible for us to land. Once that landing site is selected, our guidance will steer us towards that location. There's also an interesting systems uncertainty problem here, which is that the best Cassini data of the area in which we're targeting is roughly kilometer scale. So we don't really know what the hazard distribution is where we're going to land. We can only use the best analogs and models possible and be conservative when we're doing that. It's an interesting example of the collaboration between some of the world's experts on Titan that are scientists on the Dragonfly team, helping define that design and verification strategy for some of our algorithms like this. Next slide, please. We also have that MMRTG, which once we get to Titan will provide us something less than 100 watts of continuous power. The problem is that we need a lot more than that to fly even on Titan. So we need to carry a very large battery and charge that battery for many hours from the MMRTG power and then go fly. But in order to charge that battery, we want to give it as much juice as possible to make sure that we can charge it in a reasonable time. And that means that we have to power off almost all of our avionics, including all of our flight computers. That means that more than most of the previous missions, our flight software needs to be capable and verified to constantly be powering off and powering back up again, saving all necessary state. That includes a lot of state that we haven't done on some of our prior missions, like downlink file transfers, navigation state, and so forth. As I said before, we also need to be able to boot fast to respond in hibernation. There is a system that will be awake constantly that will be monitoring a few choice telemetry points, such as from our thermal system, but that's not designed to actually respond to any of those faults. It'll wake up the flight software if it needs to, and the flight software needs to be able to boot fast, recognize what the problem is, and potentially take action. It's also true that that boot sequence needs to be fault tolerant at a system level. You can imagine if we were on our A-side flight computer and then we went to sleep for a week, and then the A-side flight computer didn't boot back up again. So our boot sequence at a system level needs to be fault tolerant so that we can always wake up if there's anything possibly working. Next slide, please. We also have very low bandwidth being so far from Earth. Our maximum downlink rate at Titan is going to be approximately 2 kilobits per second. And of course, that's not continuous. The avionics being on drains the battery, and the radio power transmitting drains the battery even faster. We also have a 16 Earth day Titan day, which we call a T-Sol. So that's roughly a 1 Earth week day and 1 Earth week night. And during the nighttime, of course, Titan's in the way and we can't talk to Earth. So our total mission science downlink is estimated at about 6 gigabits, and that includes all of the images that we may take. So our downlink and power, which are related, are very precious resources. Every ounce of energy that we save is potentially more time that we can be powered on and transmitting data. So from a flight software perspective, we have to compress our science data and all recorded telemetry. We're also doing deep looks at all of our telemetry formats and protocol overheads to make sure that we're not wasting any bits. We're also looking at ways for anomaly investigations to query the lander for data very precisely so that we can ask the lander for only the data we want in only the timeframes that we want to make sure that we can get timely information down to the ground. Next slide, please. We also have a very long round trip light time. It's approximately 3 hours round trip between Earth and Saturn. So for a 30-minute flight time, we have to be able to send the go for flight, and then everything after that, including the entire flight sequence and landing, must be fully autonomous. We also have a long history at APL of using the CCSDS file delivery protocol for file uplink and downlink. And Dragonfly will set the distance record for CFDP when we arrive at Saturn. We have an 8-hour DSN contacts and a 3-hour round trip light time. So we're going to need to configure CFDP and make sure that it's efficient for use in those situations. Those of you that may be familiar with CFDP know that it takes some configuration in order to get the most bandwidth out of it. It's also worth noting that the last mission to launch with a longer round trip light time was New Horizons in 2006, which was also built here at APL. So we're trying to gather as many lessons learned as possible from operations and flight and ground software design. It's very important and worth noting that we actually have multiple people from the New Horizons operations team and software team already working on Dragonfly, and their expertise has been invaluable. The New Horizons Pluto flyby, though, was also largely time sequence commands. You could know within a reasonable certainty where the spacecraft would be at a given time and know how to point it in order to take an image, for example, of the target that you wanted. That won't work, though, with closed loop Titan flight controls, where we can't predict in advance exactly where we will be or where we'll be pointing during a Titan flight. So there's going to be a different model needed for that. Next slide, please. So all in all, we're going to explore a very unique world with a very unique vehicle, and it's going to have some unique flight software on it. It's truly exploration and discovery, intermixing some enticing science with difficult engineering. We hope to learn way more about Titan and by extension Earth in the late 2030s with this vehicle. And for any time left, I'll be happy to answer some questions.
All right, that was fantastic, Brandon. We do have 4 questions in the Q&A chat. The first one from Guillermo, is the hazard map from the LiDAR processed on board or on ground back on Earth?
It's all processed on board, and it has to be because our landing sequence, our EDL sequence, actually is the first time that we're going to be using those rotors and flying around on the ground. So we release from our back shell somewhere above the surface of Titan, and then we have to be able to fly away from our back shell and then do a completely autonomous landing without any guidance whatsoever from Earth. So we have a sequence that we're planning that will allow us to do a low altitude pass of wherever we happen to be over, and then that'll allow us to build up the hazard map to find our first landing site.
All right. Next question from Peter Fettelman. What kind of faults do you imagine happening during hibernation?
Yeah, that's a great question. If I had the final answer for you, I'd love to have it. The short version is that one of the main faults is relating to our thermal system. As I mentioned, Titan is very cold, and of course we have atmospheric conduction that isn't present on most spacecraft. So our thermal system is very important, both during the cruise stage and while we're on Titan's surface. And that thermal system, if there's any faults in it, the flight software may need to respond by switching over some hardware configuration.
All right. Next question from Eddie Benowitz. Do you have any plans to split the flight software across multiple processors or FPGAs, given the control rates and the in-flight image processing needed for navigation?
Yes, we do. And there's actually another talk upcoming later in the workshop. I don't remember exactly when it is, from Dimitri Becker, and he'll be talking a little bit more about exactly that and some of the architecture that spans both Dart and Dragonfly for doing some of that image processing. So more details later in the workshop.
And it looks like Dimitri's presentation is Wednesday at 2:35 p.m. Eastern Time. All right, next question from Leonidas. Which CCSDS compression standards are you considering? Are you planning on using an ASIC accelerator or select a powerful enough hardware platform that you can perform compression in software?
Yeah, that's an excellent question. The answer is that we haven't finalized our compression algorithm selection yet, although we do have a few options and we have planned an open trade study to look at future ones. Because we won't be transmitting constantly and our downlink bandwidth is very low, we're not expecting to need a hardware accelerator for any of our compression because the data volumes will be low enough that we'll be able to compress them offline and have them ready for the next downlink pass.
All right. Okay, so the next question from Nicolo. How do you plan to convert your fault detection and recovery strategies to software? Is there an automatic tool?
It's an excellent question. The answer to that one is a little bit beyond the scope of this talk, but APL has a long history with our rule-based autonomy engine that we've flown on many prior spacecraft, including Parker Solar Probe. And the Dragonfly will mirror most of those developments.
Okay, this is all right. Next question from Steven Stolper. Given the drift of the IMU, how will the spacecraft point to the high gain antenna accurately?
Yeah, that's another really excellent question. We are planning to be able to tell Dragonfly where it is globally on the surface of Titan and maintain enough knowledge on board for where Earth would be in the sky and a precise enough timekeeping reference such that we should be able to find Earth fairly accurately. We're also planning for some contingency cases, though, where Dragonfly may attempt to point the HGA, not find Earth, and then have to execute an Earth search algorithm. We're still working through the details of those algorithms, though, so we'll have to see where that ends up in the future.
All right. Next question, are you using any type of machine learning to train the vehicle to find a safe landing zone?
That is an excellent question, and I will actually defer that to Dimitri's talk on Wednesday to answer in a bit more detail on exactly how the image processing will work.
All right, and we'll take one more question from Kevin Ortega. How do you handle when the saved state becomes corrupted?
When we figure that out, I'll let you know. We're definitely looking through potential fault cases that includes things like our non-volatile memory being corrupted, having to be able to do configuration checks on all of that data and flight software configuration. We haven't worked through those fault responses yet, though, but it's certainly something that we're thinking about.
All right. with that, we will call it a day.
Okay. Thank you.
Thank you very much, Brandon. That was an excellent talk. All right, so I want to give folks a reminder that Brandon is also our technical chair at the Flight Software Workshop this year. So we really are flight software engineers putting this event on. And incidentally, I met Brandon for the first time at the last Flight Software Workshop in Huntsville, Alabama. So that's networking at its finest at the Flight Software Workshop. So I hope that today and over the next few days, even though it's a virtual event, that we have some opportunities to network. And of course, it's about meeting people and sharing ideas. And I loved what Steve Thibault said in our keynote talk today about sharing bread results in half the amount of bread for ourselves. However, sharing ideas results in an even better idea than what we started with. I'd like to thank our featured speakers and our keynote speaker, our sponsors, and all of our technical speakers for today, tomorrow, and then the subsequent days. The schedule, again, is posted on our website, and the different days are on different tabs above the schedule. Tomorrow, we are starting at the same time at 11:30. If you are a presenter, you can connect at 10:30 if you were unable to join for any of the orientation sessions that we've had so far. And we'll go through some of the logistics of the event and how we've been operating this. Our keynote speaker tomorrow is Kevin Bell, Vice President of Space Program Operations at the Aerospace Corporation. So I'm looking forward to a good day of technical presentations tomorrow as well. If you have any questions, reach out to us at spacefsw@gmail.com, and you can also ask questions using Slack. There are various channels for getting through to the right people. With that, we'll conclude our festivities for today. Thanks everyone for making the Flight Software Workshop a successful event, and we'll see you all tomorrow.